That number is the standard the data center industry is built around. It is called five nines availability. It means a facility can be offline for a total of 5 minutes and 15 seconds in an entire year and still meet its contractual obligation. 5 minutes in a year of 525, 600 minutes. That is a failure budget of 0.001%. Achieving that number requires a specific engineering philosophy, redundancy. Every critical system must have a backup, and in the highest tier facilities, every backup has its own backup. Today, I am breaking down the three main redundancy architectures used in data centers, what each one protects against, and why choosing the wrong one can cost millions. At its simplest, redundancy means having more capacity than you need so that if a component fails, the remaining components can carry the full load without interruption. In a data center, the critical systems that require redundancy are power supply, cooling, network connectivity, and fire suppression. If any one of these fails completely, the servers go down. The question is not whether to have redundancy. Every serious data center has it. The question is how much. N+1 is the most common redundancy level. N represents the number of components needed to handle the full load. +1 means you add a single additional unit as a spare. If a data center needs 4 cooling units to maintain the right temperature, an N+1 design installs 5. If one fails, the remaining 4 handle the load. The facility continues operating without interruption while the failed unit is repaired or replaced. The same principle applies to power. If the facility needs 3 UPS modules to support the IT load, an N+1 design installs 4. One can fail or be taken offline for maintenance without affecting operations. N+1 is efficient. It provides protection against a single component failure with minimal additional capital cost, typically 15 to 25% more than the base system. But it has a limitation if 2 components fail simultaneously, or if one fails while another is being maintained, the facility loses its redundancy margin. One more failure after that, and the servers are at risk. For many enterprise applications, N+1 is sufficient. For mission-critical infrastructure where any downtime has catastrophic financial consequences, it is not enough. 2N doubles everything. Instead of adding one spare component, you build 2 completely independent systems, each one fully capable of supporting the entire facility on its own. 2 utility power feeds from different substations, 2 sets of transformers, 2 sets of switchgear, 2 UPS systems with independent battery banks, 2 separate distribution paths, all the way down to 2 power connections at every single server rack, each connected to a different path. If the entire A-side power system fails, every component from the utility feed to the distribution board, the B-side takes over instantly. The servers never lose power, the switch is seamless because both paths are live simultaneously. This is the architecture used by hyperscalers and financial institutions, where an hour of downtime can cost tens of millions of dollars. The trade-off is cost. A 2N design adds 40 to 60% to the electrical infrastructure budget compared to N+1. You are building 2 of everything, only one of which is active at any time. The other sits there, waiting, costing money. Every day is not needed, but the insurance is absolute. A 2N facility can survive the complete failure of an entire power path, including the utility feed, without any impact on operations. That is a level of resilience that N+1 cannot match. Some facilities go further. 2N+1 means two independent systems, each with an additional spare component. This provides protection against a complete path failure plus a simultaneous component failure on the surviving path. This is the highest tier of data center redundancy, corresponding to Uptime Institute's tier classification, fault tolerant. The facility can sustain any single failure, including a full path failure, without impacting the IT load. Tier IVOR facilities are rare and expensive. They are typically built for government, military, financial exchanges, and the most critical hyperscale operations. The construction cost premium over Tier 3, which is typically N+1 or 2N, concurrently maintainable, can be 30 to 50%. Redundancy is not just about power. Cooling systems follow the same philosophy. An N+1 cooling design has one extra cooling unit. A 2N design has two completely independent cooling loops, each capable of cooling the entire facility. Some facilities split the data hall into independent thermal zones so that a cooling failure in one zone does not affect another. Network connectivity is also redundant. Dual fiber entries from different carriers routed through different physical paths into the building. If one carrier or one route fails, the other maintains connectivity. Even fire suppression has redundancy. Gas suppression systems have primary and reserve cylinder banks. If the primary bank fails to discharge, the reserve bank activates automatically. The ultimate test of redundancy is not a component failure. It is a full facility failover test during commissioning. Engineers deliberately disconnect the main power supply and verify that the entire building transfers to backup power without dropping a single server. Then they deliberately fail the backup and verify that the secondary backup takes over. Every Tier 3 and Tier 4 facility runs this test before it goes live. If it fails, the facility does not open. In a 2N facility, the engineers go further. They fail the entire A side, run the building on B side for an extended period, then restore A and fail B. Both directions must work flawlessly. The next time you stream a video, make a bank transfer, or ask an AI a question, the response arrives in milliseconds. Behind that speed is an engineering philosophy that assumes failure is inevitable and designs around it. N+1 survives a component failure. 2N survives a system failure. 2N+1 survives a system failure plus a component failure on the surviving system, and 5 nines, 99.9999%, 5 minutes of downtime per year, is the result.